Are you curious why I have chosen this topic today? And let me give you the soundest advice which will immensely help you to make you the best version of yourself. And I welcome all the brilliant brains to follow me till the end so that you will be incredibly benefited. And see here, let's get started with today's topic, that is on integration using residues. And this is the integral of the type integral minus infinity to plus infinity e power I mx f of x into dx. So this is the most important question. See, please do follow till the end so that it will be very helpful for your preparation. So now in this video, we have to evaluate integral minus infinity to plus infinity sin x by x square plus 4x plus 5 into dx using the residue theorem. So this is the closed contour which I'll explain soon. So here is the solution. So we have to consider the integral. So this is in terms of x. I'm changing this in terms of z. So this is integral c f of z dz can be written as sin z by, this is z squared plus 4z plus 5 into dz. So here talking about this contour. See, what is this contour? C is a contour consisting of a semicircle. So this is a semicircle CR of radius R and the bounding diameter minus R plus R. So this is a semicircle. So this is the diameter. So this is the bounding diameter minus r to plus r, and this is a semicircle with center 0 and the radius r. As this is a closed contour, we have to evaluate the integral within this one. So now integral c f of z dz is split into two parts. One is through the real axis minus r to plus r, as this is real axis f of x into dx, and next through this line, that is integral CR f of z into dz. So we have to evaluate these two values and we have to add up these two so that we'll be getting the final result. As you know that e power I theta value is nothing but cos theta plus I sin theta. So here e power I z value is equal to cos z plus I sin z. So in the question we have sin z. So in place of sin z, I am writing, as this is the imaginary part and this is the real part, I am writing this sin z as the imaginary part of e power iz. Clear? So in place of sin z, I am writing as imaginary part of e power iz. So that our f of z is transformed as this one. F of z is equal to e power iz by z squared plus 4z plus 5. Now we have to use which theorem? Residue theorem. So for finding the residue theorem, so we need the poles. As usual, for finding the poles, we have to equate this denominator to 0. That is z squared plus 4z plus 5 is equal to 0. So I have to make up the roots with this. So in order to make the roots, as I have a formula for the roots, that is minus b plus or minus root over this is b square minus 4ac by 2a. So here a value is 1, b value is 4 and c value is 5. And see, if I substitute, this will be minus b, that is minus 4 plus or minus root over b square. So 4 square is nothing but 16 minus 4 into a into c, that is 4 into this one is a and this one is c by this is 2a. So this value is 2 and z value is minus 4 plus or minus this is a 16 minus 20 by 2. So z value will be minus 4 plus or minus. So this will be minus 4 plus 2 and z value is equal to this is minus 4 plus or minus this value is 2i by 2. Clear? So if I take 2 common, this will be minus 2 plus or minus I by 2. Now I got the two poles as this is minus 2 minus 1 comma this is minus 2 plus 1 are two simple poles. These two are simple poles. So now we have to check whether these poles are within or on or outside the given contour, as this point is minus 2 comma minus 1 and this is minus 2 comma plus 1. And let's get a verification that whether these points are within or on or outside the given contour. So this is the bounding diameter and this is 0. So this value is x-axis, this is y-axis, and see this value is 1. So this is minus 1 and this value is plus 1. So this is minus 2 and this value is plus 2. Clear? And this value is 1 and this value is minus 1. So if you check this, so x-axis minus 2 and y-axis minus 1. So down here. So here is minus 2 minus 1 is point is here down. And next one minus 2 minus 1. So this is minus 2 and this value is plus 1. So this is here. So this point minus 2 plus I point is inside the contour and this value is minus 2 this is minus I. So this is minus 2 minus I is outside the given contour. So as we need only the interior poles, so this is within the pole, that is minus 2 plus I is inside and this one is outside the pole. So this one is outside and this one is inside. Now we need to calculate the residue for this interior pole. So how to find the residue? As this is a simple pole, so for finding the residue, what we have to do? For residue at the interior pole, residue of f of z for the interior pole z is equal to z naught is nothing but limit z tends to z naught. This is z minus z naught into f of z. So what is the interior pole here? This is minus 2 plus I is the interior pole. And what is our f of z? F of z is very clear as this one. And now if I substitute, this value will be residue of f of z. For the interior pole, this is minus 2 plus 1 is equal to, this is limit z tends to minus 2 plus 1. This is limit z tends to, this value is minus 2 plus 1 into f of z, that is e power iz by, this is z plus 4z plus 5. So in order to calculate like this, there is a formula here, as this value is f of z. So f of z value is e power iz by, this value is z square plus 4z plus 5. So this value I have to take it as phi of z and this value as xi of z. For the numerator phi of z and the denominator xi of z. And now here is the formula. So which formula I have to apply? So I have to apply a formula that, see, here is the formula, that is residue of f of z for z is equal to z naught is equal to, this is limit z tends to z naught. The formula here is phi of z is as it is and we have to make a derivative for the denominator and again substitute the value here. Again we have to substitute z naught value. So what is our z naught? So z naught value is the interior pole minus 2 plus I. So now this is going to become, so this is the second method of finding the residue, that is z is equal to minus 2 plus I. This is limit z tends to minus 2 plus I. What is our phi of z? For the derivative here, so as it is we have to write like this, and here the derivative is, so this value is phi dash. The derivative of the denominator is nothing but 2z plus 4 for the point this one. So here the point is I times of, this is minus 2 plus I by 2 times of, here the point is minus 2 plus I plus 4. So in the second method I have calculated this residue and this will be, if I multiply, this will be minus 2i, I square, this is minus 1 by, so if I still multiply this one, this is minus 4 plus 2i plus 4. So after cancelling this one, so this is minus 2i into e power minus 1 by, this value is 2i. So this is nothing but the residue of f of z for the interior port, z is equal to minus 2 plus I. So this is for the interior pole, this is our residue value. So after getting the residue value, what we have to do? So we have to apply this in the residue theorem. So what does our residue theorem statement states? According to our residue theorem, let me explain you. This is our residue theorem. So according to our residue theorem, so this is very clear that this is integral C f of z into dz is nothing but, this is 2 pi I times of sum of the residues at interior poles. Therefore, integral C. So here, see, this one is integral C f of z dz is equal to, this is 2 pi I into, the value here is this one, this is e power minus 2i, this is e inverse by 2i. This is 2i. Now if I cancel this 2i in the numerator as well as this denominator, this is integral C, this is f of z into dz is equal to pi e power minus 2i by e inverse is nothing but pi by e power minus 2i. So here what is our contour? So the contour here is like this. So this is the closed contour from minus r2 plus r, and this is 0, this is x-axis and this is y-axis, and this is a semicircle with center 0 and radius r, and this is through the line. See, this is the closing line. So I have to split this in terms of two parts. So the first part is like this, minus r2 plus r. So this is from minus r2 plus r through the real axis f of x dx, and this is minus r2 plus r, and this is through the CR, the semicircle. That is f of z into dz is equal to pi times of e power 2I by 2. And this is our first question. And next, as r tends to infinity, as we tend r to infinity, as if you tend r to infinity, then see, this will be minus infinity to plus infinity, minus infinity to plus infinity f of x. F of x is nothing but the real part of e power ix by, see here I am showing you, this is our f of x, e power ix by, this is x square plus 4x plus 5. This value is x square plus 4x plus 5 into dx plus integral CR. This is f of z into dz value is equal to, this is pi e power 2I by 2. And now as r tends to infinity, this value is 0. As I have given you a crystal clear clarity in my previous videos, after keeping z is equal to r into e power I theta, so we'll be getting this value as 0. And what remains here, this is minus infinity to plus infinity e power minus x by. Please go through my previous videos. I have uploaded why this function is becoming 0 after the substitution. So many videos I have uploaded, and this is the final video. If you follow those videos, so you will be getting a clarity. That is pi e power, this is 2I by 2. So this is 2I or minus 2I. This is minus 2I by 2. And see, this one, I can write this as minus infinity to plus infinity. This can be written as cos x plus I sin x by, this is x square plus 4x plus 5 into dx is equal to pi into e power minus 2 by 2. So if I split this as a real part, that is cos x dx by, this is x power 4 plus 4x plus 5 plus I times of, this is integral minus infinity to plus infinity, this is sin x dx by, this is x square plus 4x plus 5 is equal to, this is pi by 2 e power minus 2I plus 0 into I times. After equating the real parts here and imaginary parts, we need the real part. Now see, e power 2I can be written as, so this can be written as pi by 2 times of, this is cos 2 minus I sin 2. Clear? This is cos 2 plus I sin 2. E power I theta can be written as cos theta plus I sin theta. E power minus I theta can be written as cos 2 plus I sin 2. So this is nothing but the real part is here pi by 2 cos 2 minus I times of, this is pi by 2 sin 2. Sin 2. Now if I equate these two, so this is the imaginary part. So here there is I and here there is I. If I equate these two, and our final answer will be, equating the imaginary part, equating the imaginary part on both sides, this will be minus infinity to plus infinity. This value is sin x by, this is x square plus 4x plus 5 into dx value is equal to minus pi by 2 into the value here is sin 2. See here, this is pi e power minus 2 by e. Here also it is e, and by mistake I have written this one. So this is also e. And this value is e, this value is e, and this is e again, e, and this is e, and this value is e, so that this value is pi by e times of sin 2. This is the final answer. Hope you all guys understand. So this is the process. If you follow my previous videos also, you will get a crystal clear clarity why each and every step has done, and you can solve any problem of this kind. So these are the most important problems from the previous question papers I have solved and uploaded in the playlist. Please go through the playlist for further details. Please leave a comment and definitely you will be answered. And if you really like, you know what to do, please subscribe to this channel, stay connected, and please share it with your friends, family, siblings, and the person you like the most. Thank you so much.